So yes, the let's see. Is this one? Yes. So I will briefly start with the participants. So this year we have so from the faculty, of course, we have collaboration with Jorge, with Remo, and also interaction with Gregory. Then the students, this I would like to comment. So PhD students, graduate students are working and have work and collaborate with us in the papers of this year is Valentina Crespi and Santiago Collazo. These are two PhD students of La Plata National University working under my direction. And then Carolina Villauro, which has ended her PhD last year. And then a new PhD student, which is Mauricio Batista Perez from Cuba. He has started also to work in the field of dark matter. We have other researchers from Argentina, which are now actively collaborating with us. Martín Mestre, Andreas Cruz as well, always with us. Then Pierre Chavani is also collaborating with us, and Florencia Vieiro and from Radio Astronomy Institute of Argentina, and Joaquín Pele now in Germany also collaborating with us. So let me start with the two topics that we have worked in this 2024, which is dark matter in the Milky Way. So the fermionic dark matter model applied to the Milky Way, where we have studied a new tracer of the gravitational potential of the Milky Way, which are stellar streams. Usually we have been working in the last years with rotation curve, but now also interesting to include stellar streams, which are powerful tracers of the gravitational potential. So we have modeled the GD1 stellar stream, which is a cold stream quite well observed, covering radial extent in the galaxy from, let's say, roughly 10 to 50 kiloparsec long. And so the result there is that I can say in words here. So we model the baryonic potential, the baryons were bulge and disks, and for the dark matter we use our fermionic core halo model, and we took 5D space-based data from Gaia DR2 survey, and together with the S stars, the S2 star at the center. So this is the first. This work is one of a kind in the sense that this is for the first time we have used two sets of data, the S2 star together with the 5D phase space of stellar stream, and ask if this overall dark matter distribution can answer for these two sets of observables at the same time. So particle masses has been worked out in the range of between 56 keV and 360 keV, implying that the dense core of this dark matter can range from roughly 1,000 Schwarzschild radii down to few Schwarzschild radii for a central object of 4 million solar masses at the center of our galaxy. So the interesting result is that this summary that I have done for the report is that this work provides evidence that fermionic dark matter is a reliable model for the central object of the galaxy. It has a mass of 2.3 10 to 11 solar masses, the whole halo, and so the highlight of the plot that I prepared for this is this one, which is the after feeding the 5D phase-space data of the GD1 stream, which is where the stream, this is this gray shaded gray bar here is where the string moves. And a posteriori comparison we have done for the rotation of the circular velocity against gradient. So interesting, the outcome is that the fermionic model, which is the yellow curve, is a posteriori comparison with the rotation curve, where we have shown that the model that can explain the S2 star together with the stellar stream data has the right decay of the dark matter profile at the boundary, let's say above 20 kiloparsec, which start to go along the data of Jiao 2023, which is the Gaia DR3 data for the rotation curve, which if you, for example, compare with the prediction in green, which is an FW, then FW, which is the state-of-the-art model that explains this GD1 stream, is totally offset from this Keplerian trend observed for the outer part of the Milky Way by Gaia DR3 data. So this is first very interesting result. Now we are.
By the way, Carlos.
Yes.
I will select at the end of our presentation 7 topics which, in my opinion, have signed the scientific development in IGRANET in 2024. And if you don't mind, I would like to add this figure 3.1 in the 5th classic result, which I will mention, which is really crucial because it shows so beautifully the presence of the degenerate core for the core and the semi-classical part of the dark matter in the halo, which is spectacularly verified by this data. Therefore, I will use that, remind me to put in quoting, of course, the Mestre paper and all the other paper in our summary, in my summary. Go on.
Yes. Thank you, Remo. Yes. So, and more work. Then I want to say that this is because let me just remark this, because this paper was not aimed to the rotation curve. This paper was aimed to the stellar stream together with the S2 star. As an outcome, just by a posteriori comparing the behavior of the rotation curve, that has to say this best fit dark matter model, it comes up this nice matching, which tells that power law, typical power law NFW model R to the -3 in the outer part do not work well with the data. But more details will come soon. For a new work we are finishing dedicated exclusively to the rotation curve of Gaia data, and the result will be, of course, along this line, but with new constraint for the particle mass that you will see soon. So next work was regarding Milky Way, is regarding the image of the central object at the galaxy center. So we were interested, after Event Horizon Telescope image done for Sagittarius A star, we took the challenge to make relativistic ray tracing for an accretion disk, which was solved within, consistently solved within our dark matter central object. So we put an accretion disk, alpha disk, going around this core, and we have shown, let me go to this next slide, that we have investigated whether such cores can produce observational signatures similar to those of black holes when illuminated by this accretion disk. So as I said, the image were done and the spectra were done with the source as a fermion core instead of a black hole, using this general relativistic ray tracing and assuming that the radiation comes from standard alpha disk or saturation jive disk. This is a remark here because we know that alpha disks are typically applied to active like galaxies, so not as in our galaxy, which is non-active galaxy. Though this was as a proof of concept to see if the image coming out from the radiation of these alpha disks around 4 million times solar masses can already have the expected size of the shadow-like region inside. And the result was positive. Here is the plot, here in the top. Maybe I can zoom a little bit more. So you see that, for example, for this example of 300 keV particle mass, the core, the central core of 4 million solar masses is close to its critical value of collapse, though yet relatively far, because the critical mass, particle mass is 370 keV, so we are still not entering the critical regime. And interestingly, the size of this shadow-like region is of the order of tens of microarc seconds, which is the scales observed by the Event Horizon Telescope. Of course, a precise comparison with EHT we need a more realistic accretion disk, which we are starting to study. It has to be, let's say, optically thin, but this is under development. This work. So this is was a very first result, which is
you evaluate the bolometric luminosity of such a ring.
Yes, this is in volumetric intensity. This is normalized with this Imax in the upper band. So yes, the numbers of the intensity depending on the angle of the disk respect to us is computed for this case. Yes. Then I can tell you the right values.
We are very interested in this result, and
yes, because at least now we can say that not only the compact cores not only can explain the S stars, as we have been showing with the collaboration with Edward and Jorge and in the team in the last years, but now the core can cast image of sizes similar to those observed. So I think this is makes this alternative even more solid as a possibility.
There is any limit on the Eddington luminosity of this object?
Well, a limit. I mean, this object, in the case of Sagittarius A star, has to be very low limit on power, the Eddington limit power, because we know the luminosity is order of magnitude less than values as in active galaxies. I don't remember precisely the number, but I think it's orders of magnitude below what. I think it's 6 or 7 orders of magnitude below what you typically obtain in active galaxies at Eddington.
But since you have the bolometric, it will be worth it
to check precisely how below.
Of course, the Eddington has to be very small. But still, the black hole is very big. It's 10 to the 6 solar masses. Well, we are working on that. We would like to have your feedback.
Yes, yes, sure.
We will work
Uh,
together on this topic.
okay, and I will tell a bit more of this image for typically low luminosity AGNs later on. So, and yes, so this is the highlight of the Milky Way of this year, of last year, sorry. And now the next topic was supermassive black holes, nature and formation channel. So, with this same theory of self-gravitating fermions within GR at finite temperature, with Jorge we have and Remo we have done a very nice job last year after many years of fighting with the possible role of baryons accreting onto this fermion core. We could come up with a model where the initially stable fermion core start to capture baryons and start to capture baryons which trigger after a threshold density and a threshold accretion and velocity triggers the collapse of the core into a black hole. This is summarized in this plot here. This is the traditional, maybe to zoom in. Yes. So this plot is the traditional mass versus central density. So the upper curve in light gray is the core, the very dense degenerate core of fermions without any baryons, and so this curve and the lower one is when the core has already 0.8 fraction of baryons. So the key point here is that when you can start with from here, from where the dashed line start in the light gray, and while start to accrue baryons in a given delta time, in a given time window that we can calculate, the diameter core is accreting baryons until it reaches the maximum in the mass, in the total mass central density, and so reach the turning point of gravitational collapse. And so the interesting point is that with typical baryon densities and dispersion velocities as observed in local universe and also in some colliding galaxies at the center, the collapse, so the time scale of gravitational collapse of the core can be reached in a fraction of a giga-year. So let's say let's see if I put the next plot. Yes. So here I show the evolution of the mass. So starting, for example, in the blue curve, for example, with a central diameter core mass of 2 times 10 to 7, this baryon-induced collapse calculation shows that in 0.6 giga-year, so 600 mega-year, collapses towards a black hole of roughly 3 times 10 to 7, as observed typically in the high-redshift universe observations of many low-luminosity supermassive black holes as observed by James Webb. Also very interesting is the potential application to the so-called little red dots, because the bulk of them has masses quite relatively lower than observed in the local universe. For example, from several 10 to 6 up to several 10 to 7, typically solar masses. And so here is an open field of research, because this new challenge has shown that can form those objects, be in a black hole, but also interesting to think that if conditions of density and environment are not acquired, they can remain as a very dense core, without collapsing, This may open the interpretation that the nature of the little red dots can be these very dense dark matter cores where halo are born at, or close to Earth at that high redshift. And finally, the highlight is a few comments about the related that I said is the nature of the central engine in low luminosity AGN. In the paper of Giugiaro, Carolina Giugiaro, we finished her PhD a couple of years ago. Finished the master a couple of years ago. Now he's collaborating with us. With her, we did a nice work where, let me go to this plot, where we put an accretion disk. We extended, generalized the solution of circular engineering disk, but not around a singularity, a black hole, but around a very compact object. And we calculate the energy spectrum. And we demonstrate, this is a nice example, that for example, this BH is a black hole and it exists, for example, for 200 keV particle mass. Let me show here. Zoom out a bit. So for 200 keV, example, which is the solution in red, the B2, you can have a luminosity spectrum indistinguishable from the one of a Schwarzschild black hole. And this is very interesting because it means that, even though the black hole is clearly more compact than the core, given that the accretion disk can enter somewhat inside this fermion ball, the efficiency can be of the order of Schwarzschild or even higher, and the spectrum is indistinguishable. So this is from an observational point of view. This is very important. And finally, the images, characteristic image of this course around this 10 to 7. These 10 to 7 objects, dark matter object, are displayed here. And maybe just a comment that in the lower panel, you can see, for example, in the lower right panel, when you see edge on, the more compact the core, which in this case is for 200 keV, because it's close to the critical mass of 10 to 7 solar mass black hole. The more compact solution develops this relativistic effect of light, showing how light appears also from the back, right? In some analogy to what is observed or predicted by a Schwarzschild black hole. Of course, the light bonding in a black hole is more prominent than in a dark matter, because the maximum deflection angle in this core are a fraction of pi, while of course in a black hole you can reach 2 pi, right? Circularization. That will be all. So 2024 we have done 5 publications and 2 submitted papers, so 7 papers in total, and the other work submitted will be presented next year. So I didn't include in this. Thank you very much.
Thank you so much for this very, very beautiful talk.